So in this video 10.7, we're going to talk about the kinetic molecular theory. The kinetic molecular theory simply takes about 5 or 6 statements and tells you everything that you know about ideal gases, or about gases that we've learned thus far. These are the statements right here in bullet point version. I'm going to simplify them and give you some things you can write down about each of them as well. But if you'd like to go through and write down each one of these, you can as well. So first of all, gases are made of particles. The particles are far apart and very small. We can ignore the size of the atoms or molecules that make up this gas compared to the volume that they contain. These gas particles undergo collisions, and there's no energy loss during these collisions. They collide with one another, or they collide with the walls of their container or whatever's inside of their container, and that's what causes pressure. They have no attractive forces. They don't attract to each other or the container that they're in. We treat all gases the same. We treat nitrogen, oxygen, carbon dioxide the same, and this allows us to treat them all with Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. And mathematically, we'll come really close to what they are in the real world. Pressure is caused by the collision of gas particles. The more collisions you have, the more pressure that you have. If you have lots of collisions, you have lots of pressure. Temperature is the average kinetic energy, or the measurement of the average kinetic energy of the gas particles. And if you have more kinetic energy, more energy of motion, then you have more collisions, and then you have more pressure. So ideal gases assume all of these things. And we've assumed throughout this entire chapter that we've had ideal gases. And ideal gases happen when we make these assumptions right here. But what about real ones? Well, real ones are really close to this, except there's two parts. The particles do in fact have some size. It's a very, very small size, but they have some. And secondly, the particles do attract a little tiny bit, but they do attract to one another as well. And these two pieces can actually be mathematically dealt with if you have an adjustment for real gases in PV equals nRT or the other ideal gas equations that we use. So what makes a gas act as an ideal gas or act as a gas in itself? Well, you usually hear two things, high temperature and low pressure. Well, why high temperature? Well, if you have a temperature that is really, really high, then things are going to be gases, because once they start to get cold, then things start to become liquids or solids. And so that's why you want gaseous things to be at high temperatures. Secondly, you want things to be at low pressure, or gases to be at low pressure. Because if you take a gas and you squish it, then the particles go closer and closer together, and eventually they'll become a liquid or a solid. So I'm going to pull up a YouTube video that actually takes all of these pieces about ideal and real gases and the kinetic molecular theory and the ideal gas laws, ideal gas and combined gas equation, and puts it together for you. I really encourage you to watch it 3 times and just get the lyrics down, because then you have all of these pieces of the kinetic molecular theory in your brain already. Here we go.
Gases made of molecules that are far apart and small. They don't lose their energy when they hit container walls. They travel in a straight line, no changing from their course. They move faster when it's hotter. They have no attractive force. Rock me, Avogadro, rock me, Avogadro, rock me, Avogadro, with gas laws. Gases that behave like this are often called ideal. Which gases are most like this, though they are very real? Hydrogen and helium, the smallest gases on the chart. High temperature, low pressure will spread them far apart. Rock me, Avogadro, rock me, Avogadro, rock me, Avogadro, with gas laws. behave like this. Treat them all the same. It's Avogadro's hypothesis that given it a name. Equal volumes of different gas, if they have the same TNP, will have the same number of molecules of gas in each, you see. Rock me Avogadro, rock me Avogadro, rock me Avogadro with gas laws. The mass of each gas molecule is weighed in AMUs. We need to turn that mass to grams, which we can better use. You need Avogadro's number. That's something that we've heard. A mole is 6.02 times 10 to the 23rd. Rock me Avogadro, rock me Avogadro, rock me Avogadro with gas laws. Because we treat each gas the same, each one that's on the list. Real gases have attractive force, pretend they don't exist. We can use the gas laws with each and every one. So go get your calculator out and prepare to have some fun. Rock me Avogadro, rock me Avogadro, rock me Avogadro with gas laws. Whether you use Boyle's Law or Charles or Gay-Lussac's, you can use them on any gas. You won't get no flack. Thanks to Avogadro, we can treat them all the same. And that is why I wrote this ditty in honor of his name. Rock me Avogadro, rock me Avogadro, rock me Avogadro with gas laws. Rock me Avogadro, rock me Avogadro, rock me Avogadro with gas laws. P1 over T1 equals P2 V2 over T2.
So there we are with the kinetic molecular theory. I encourage you to go back and watch the video a couple of more times. Learn the pieces that make gases be gases and the pieces that make them not be ideal gases, and that they exist at high temperature and low pressure. Best of luck.